Let's continue going further into the future. We've probably reached about 60 millichopras on the wackiness scale now, but some of this works, in labs at least. I wanted to talk to you about quantum computing and quantum architectures. These devices currently look again like the very early transistors, the early mercury delay lines, very large things in labs, maybe just computing with a few, we don't call them bits now, we call them qubits in quantum world. But there are companies being formed to try and commercialize this already, and it's something that may have to come along to replace the end of Moore's law. It's something you may have to work with later in your career. You can actually dial into an IBM website, I believe, now from Lincoln and run a program on a real quantum computer over the network. So before I introduce quantum architecture, we need to talk a little bit about quantum mechanics in physics. Really well done to the rest of you who are still here in part 2 of this. Again, more than last year. We're obviously not going to do the whole mathematical framework of quantum mechanics. You would need to take another course for that. But I want to give you at least the basic concepts that enable you to understand roughly what is going on in a quantum computing device. So I'm going to do this in 2 steps. This is a cartoon version. This is not correct. It is here to introduce the basic concepts, and then we'll make it a little more accurate in the next slides. Okay? So I really hate to be the person who tells you this. The real world is not the way you think it is. If you put this cat in a box, it can be alive and dead at the same time. Objects you think are real are not real in the way you believe. It was famously illustrated, this is called Schrödinger's cat. It's a thought experiment. This is not a real experiment. It's not been tested on animals. It's a thought experiment. You can, in theory, put this cat in a sealed box and you put a radioactive substance over here. Radiation is a decay. It's a completely random, unpredictable decay when one of these particles comes out. At a random moment, this particle can be emitted from the radioactive box, and it will be picked up by this detector. The detector is attached to a hammer, and the hammer smashes a glass full of poison liquid or poison gas, which in turn kills the cat. Okay? And in theory, if you are standing outside the box and you have sealed the box fully, not only do you not know whether the cat is alive or dead at a point in time, but it does not have any meaning to describe the cat as being alive or dead. It exists in what is called a superposition of states, which can be viewed as being in a mixture of parallel worlds. In one world, the cat is alive, and in one it is dead. When you open the box and you look at the cat will then decide whether it wants to be alive or dead. And so this parallelization of realities you've created collapses. It collapses down to a single version, and you will see the cat being alive or dead. Okay? Not only is it both alive and dead, but there are numbers associated with them. So in our cartoon version, you can associate these with probabilities. You might set this up with a highly radioactive substance or a less radioactive substance. So for example, the cat might be 80% alive and 20% dead. These are not just beliefs, these are actual physical states of the world. And there are experiments, probably not on actual cats, but on particles, that demonstrate that both of those realities do exist in a sense. They can both have an effect on the reality that you are in. You can show that they are both there. Okay? That was a lot to take in one slide. Let me give you a more correct version of this. I do not expect you to follow the mathematics on this. If you're interested, I've put some links on the slides to chase it up, but I at least want to give you a flavor of what it looks like so you know that it's there and you know where to look later in your studies. So there are 3 basic concepts going on here. One is about representation. We've talked about data representation already, like putting numbers in registers. This is a representation of the world. And the concept here is that objects can exist in a superposition of states, so multiple forms of reality at once, the cat being both alive and dead. These worlds, they don't have probabilities associated with them. I lied on the previous slide. What they have are what are called amplitudes. Amplitudes are complex numbers. Anyone done complex numbers? Square root of -1? Yeah. If you take the square root of -1 and call that I, and then start doing arithmetic with I, then you create this extra number system called complex numbers. Every state of reality, such as the cat being alive and being dead, has one of these complex numbers associated with it. That is a real number. That's 1 over the square root of 5, and this is a complex number because it's got I in it, where I is the square root of -1. If you've not seen complex numbers before, try and think about what the square root of -1 might actually be. So this is the basic representation. You have to choose these numbers so that if you square them all and add them together, you get 1. Don't ask why. That's just the way the world is. So they're a little like probabilities. They're a little bit like the square roots of probabilities. So that's representation, step 1 of 3. Step 2 of 3 is processing. How did these representations evolve over time? What's the equivalent of taking a register and putting it through some logic gates? Well, the laws of quantum mechanics tell us that you can operate on these representations with what are called unitary matrix operators. Have you guys done matrices? Have you done rotation matrices somewhere? Yeah? A unitary matrix is a little like a rotation matrix. So if you imagine this thing called the state vector, this is a vector, yeah? It's 2 numbers stacked on top of each other in square brackets. Imagine that as being a regular vector, and you can imagine this operator. In this case, it's a NOT gate. This might be representing state 0, this might be representing state 1. Let's use the cat as our binary representation. Let's say a dead cat in the box represents a 0 and a live cat represents 1, and we're going to do computation using quantum cats in boxes. Okay? So you've got 0 and 1 both have these amplitudes. If you multiply them by this, what is called a unitary matrix, it's a little like a rotation matrix, it will convert the amplitudes that you currently have into some different amplitudes. So for example, if your state vector looks like this, and you apply a NOT gate, the effect of this, can anyone tell me what the effect of this is? It's going to act as a NOT gate. It's going to invert the 2 states, okay? So we had, this was the amplitude of being in state 0, this was the amplitude of being in state 1. They're going to swap over. So state 1 is going to become the stronger state, okay? This notation is called a ket. I'm not going to go into it. You can see there's a line and an angle bracket. They go together a little like curly brackets. Roughly, you can think of this as meaning a vector. This is just saying this quantity is a vector. In this case, it's a simple vector that has 2 components for 0 and 1. One of the properties of these unitary matrices, it turns out being unitary is equivalent to being reversible. We've talked a lot in this module about reversibility. As computer science thinks a lot more about energy and power requirements, we're thinking about this closely linked concept of reversible computation. A reversible one is one where you don't lose information. That also means you don't lose heat. And so if you don't lose information or heat, you can keep all the information that is required to bring the system back into the state that it came from. You can reverse the computation. It turns out there's another application of that here, because the fundamental physics of quantum mechanics says that all these operators have to be unitary and therefore reversible. They fit together quite nicely. So representation then, I've just gone back a slide. Representation means every possible state of the world, like 0 and 1, is sitting there in one of these vectors with an amplitude. Processing means we can act on those representations with unitary matrices. And then the third and final ingredient of this is the output. This is what happens when you look at a system to read off the result. So when you open the box with the cat in it, that is what is called doing an observation. You are finding out whether the cat is in fact alive or dead. And at the point you do that, the physical world itself appears to change. Your act of observing the cat changes its state from being this superposition of alive and dead at the same time into being very definitely alive or very definitely dead. So with a little more mathematical language, we say when you look at a system in a basis, you have to take a linear algebra class to understand exactly what that means. But roughly, when you look at one of these vectors, it decides which state it is going to be as a function of those amplitudes. So you actually square them. If you square the numbers in that vector, then they become probabilities, which sum up to 1. So if we take the cat example, we can see I'm squaring the two numbers. And now you understand why I put the square roots of 5 in there as amplitudes, because I've set this up so that the probabilities do in fact add to 1. Okay? And this gives me the probability that I will actually see a live cat or a dead cat. Now, remember we're going to use this cat as our computing device. So the box is containing a 0 or a 1. Dead cat is 0, live cat is 1. So what I have now is a flip-flop-like structure. It's a memory device storing one quantum bit or a qubit of information. And when I look at that qubit, I'm going to see a 0 with 0.2 probability and a 1 with 0.8 probability. Okay? And that's not just what I see, it's what the world actually changes to become. Okay, so again, you don't have to follow the details of this. I just want to show you that it exists. I've given you some links if you do want to follow it up. Quantum mechanics has been known for most of the last century. It has evolved a couple of times. One of the major editors of the theory was Richard Feynman, of the famous Feynman lectures in physics. Lesser known are his even better Feynman lectures on computation. If you want to buy one really fascinating book in your entire degree, I strongly recommend you choose this one. It's just full of amazing ideas about computation. Even though he was a physicist, he came into computer science for a year, I think, for fun, and just does amazing computer science. But the idea he proposed, and that should be 1988, not 98. The idea he proposed in 1988 then was to, as we've seen with all these other technologies, with water, with rocks, with electricity, can we use the mechanics available to us in quantum mechanics to do computation? And what new kinds of computation would it allow us to do? We seem to have the ability for this cat to be in two states at once, being alive and dead. Could we get the live cat to go and do some addition for us and get the dead cat to do some multiplication for us and use it as a form of parallel computing? Okay? We have this idea of parallel universes. We're going to use the parallel universes as parallel computers. Seriously, this does actually work. There are lab experiments. This does actually work on it. Feynman is also famous for explaining anyone who claims to understand quantum mechanics is either lying or mad. So don't worry, you're not alone. To give you a more hands-on version of it, I wrote a quantum computing simulator. You can play with it from this link if you like. These are some examples of how you actually write a quantum program, and you can execute it in the simulator. If you really want, you can almost put this stuff onto IBM's real quantum computer on their website and run it for real. Here's a few basic commands in a quantum computing programming language then. So I first start by creating these states. Phi is just the Greek letter we use to represent a state. It's one of these things in a funny ket notation. It's basically just a vector. So I'm going to say I would like a register that represents the number 3 or 0, 1, 1. Okay? So we already know what a register's like. You know, you can have an 8-bit register. In this case, we're working with a 3-bit register. So 3 slots, 3 boxes with live or dead cats in, and it's going to represent these numbers. When I create that state vector, I can see the result is a vector. And currently, this thing, all the probability is representing the number 3. Okay, so there's a particular state of this 3-bit register where the first bit is 0, and the next bit is 1, and the next bit is 1. And all the probability is that the register is actually in that state. Okay, and there is no probability of it being in any of the other states. That's what's in the state vector. If you like decimal, there's a little command. You can do decimal to vector as well. So if I want to represent the decimal number 5 in a 3-bit register, I can call it like this. And you see now all the probability is in the 5th state, 0, 1, 2, 3, 4, 5. Okay? So there's a 100% probability that the register is in state 1, 0, 1. Okay? So these are just normal registers. These are how you could notate registers in a classical system like this. Classical means non-quantum in this context. In most of computer science, it means old. But what we can then do in a quantum computer is we can combine those states together. So this is like having a live cat, this is number 3, this is like having a dead cat, number 5. So well, it's 3 cats, isn't it? This is like having a dead cat and 2 live cats, and this is like having a live cat and a dead cat and a live cat, or so. Three boxes next to each other, okay? Actually, what's interesting here already is this notion of entanglement. Now we have the 3 boxes. You might think that each of these mixed up half alive and half dead cats are independent of each other. It's actually the state of the whole register that exists. So when I create a state like this, I'm saying create a new state of reality where we are half in this state, the number 3, and we're half in this state, the number 5. Okay? So there's 2 permutations of, what have we got? 0, 1, 1. So dead, live is one parallel world, and in the other one we are live, dead, live. Okay? What you see here is the boxes are not independent of each other. Okay? If I go and open this box, if I open the first box now and I see a number 1, what's going to happen? Okay, I know there was one reality where I had dead, live, and there's another reality where I have live, dead, live. If I go and open the first box, I know now that I'm in this parallel universe. This other one disappears. So in particular, I now know what is in the other 2 boxes. So I've only opened the first one, that was a mixture of live and dead. That has changed the reality of what is in the other 2. Okay? This even holds if I send them to different places. I could take my 3 boxes with mixtures of cats in them and send one to Mars and one to the moon and keep one here. I'm going to open the one here, and only at this point, if it's the other way, if I open it and I see a 0, I now know that the box I sent to the moon has a 1 in it, and the box I sent to Mars has a 1 in it. If I'd have opened it here and got the 1, then I'd have known the moon would have 0 and Mars would have 1. Then there's some printf formatting statements. So you can take a state vector and call a pretty print function on it, and it will turn it back into a nice quantum computing representation. So if we take a vector like this, remember this is a superposition of those 2 states. It's printing out as saying this is 0.7 amplitude in that state, in the state 3, and it's 0.7 amplitude in this state, state 3. Remember, you square the amplitudes to turn them into probabilities. So if you square both of these, then they'll be half. And then they sum up to 1. Or you can print it as decimal if you like. You can say there's a 0.7 amplitude of the number 3 and a 0.7 amplitude of the decimal number 5. This property of the boxes being linked to each other, of changing when you open one, is called entanglement. So if I observe this register, this is the thing I've created. I've added part of state 3 to part of state 5. So there's the amplitudes for those 2 states. If I observe the first one and see a 1, I know that the whole register has collapsed to 101. I know the whole number is number 5, even if they're many miles apart. That property is called entanglement. It's a fundamental property of quantum mechanics. Let's think about how much information we can fit into these registers now. So we know from classical data representation that if we have a 3-bit register, we have 2 to the power of 3 possible states, right? There are 8 states that can be, and it can represent each of these binary numbers. Potentially on a quantum device, I can create a superposition where every one of those states has some amplitude. And we could send each one of those off to do some computation in parallel. So we might, for example, make a parallel world with each of the numbers from 0 to 7 inclusive. Each world has 1 number, like on a GPU parallel computer almost. And then each world is going to do some computation with that. Each world could test whether that number is the solution to your NP-hard problem. Okay? So you might, again, take a traveling salesperson problem. If you can find a way to encode every possible route around the cities as a single integer, which you almost certainly can. You could represent it as a product of prime numbers or something. As with the DNA computer, you would then need something which tests whether the solution is there or not. This is the defining attribute of an NP-hard problem. It's one that you can check if it's a solution in polynomial time, but searching for the solution is harder. So in this case, we can put our register into 8 states. Every state the register can be in exists in one of these parallel worlds. And we're going to have a function which tests, is my number the solution to this traveling salesperson problem? And it could wave a flag if it's found the right answer. This is similar to the DNA computer idea, where we have parallel computing of all possible solutions, and in that case we had the primer molecule coming in to wave a flag when it finds the solution. As the registers get big, this scales exponentially. So if you have a 64-bit word, a quantum word, you now have 2 to the power of 64 possible states, and they all exist in this sense at the same time. Yeah, this is 10 to the 19 states, and each one of those can go off and do some part of a parallel compute job. So for example, we could put it into this parallelized state and give it a task like add 1. So if you're in world 3, you're going to add 1 and you get 4. But every possible reality does that and increments the register. Billion-dollar question, though, is how do we arrange things so that you, the observer, end up in the same version of reality as the right answer? Right, we've created 10 to the 19 possible universes. One of them has the right answer and it finds it and it waves the flag. But we would like to be in that world to actually see what the answer is. And unless we do something about it, we probably won't be in that world. We'll be in a randomly chosen world. So this remains an ongoing research area. We do not know what the right answer to this is yet. There is a kind of folk theorem around that you will only ever get a square root n speed up out of this. When this first started, people thought we could solve NP-hard problems because we could try every solution of the traveling salesperson problem and somehow be in the world where we found the right answer. The problem is getting yourself into the world where the right answer already is. And you have to do work to do that. And as far as we currently know, it seems like everything ends up with this order square root n speed up. This is shown in a quantum search algorithm. So it can search n items in square root n time. So normally when you search, you have to look at each item at least one. Again, I'm not going to go through the details of this. This is a program just to show you how simple it actually is. It's just a few lines of code if you are sitting on a quantum computer simulator or a real one. Roughly, you do something that looks a lot like a Fourier transform. This is quite similar to the optical computing idea. You can create a Fourier transform of the amplitudes of the different realities. It maps you into another set of realities where every amplitude is the Fourier transform of what was there before. You see some implementations of quantum computers that look quite a lot like optical computers as well. They can be made out of lasers on tables with mirrors and lenses and so on. So there's this quantum Fourier transform operator going on called a Hadamard, and then there's something called a haystack operator. And this is similar to the idea from DNA computing. This is a function which waves a flag if it has found the right answer. And if it hasn't found the right answer, it does nothing. So it turns out, this is time. These are all the different states. These are probabilities of being in every possible reality. If you apply these operations in sequence, you do some Fourier transforms and you do some what's called inversion about the operator. That's this waving the flag thing. You just alternate those in a for loop. This is a regular for loop. As you go through that for loop, you will see that the probabilities of the different worlds change around. So when we start, the probability of every world is the same. As we go through time, the one world that we're interested in, the world that has the right answer, its amplitude increases up to a certain point. It comes down again. It'll actually oscillate as a kind of sine wave. But if you stop this process at the right time, you have at least a very good probability, as in above 90%, depending on exactly what's going on. You have a good probability that the world that you end up being in is the same one that the solution is in. Okay? This comes as a consequence of the complex numbers in the amplitudes. If it was just probabilities, this wouldn't work. The thing about complex numbers is they can cancel out. When you see light behaving like a wave, you see it interfere with itself, and some places become strengthened, some places become weakened. What you're doing here is weakening the strengths of the worlds that you don't want, and you're trying to make these things interfere constructively to emphasize the world that you do want. So this is serious enough now that the NSA is spending a lot of money researching it. In particular, these algorithms can break the cryptography that you use on all your websites, systems used inside the SSH protocol. So if anyone actually builds one of these, they have a good chance of being able to read everyone's passwords and emails and credit card numbers and everything. Those systems are based on multiplying two big prime numbers together to get a really enormous number, and then the task is to factorize it without knowing either of the numbers. It turns out that's another application that these systems are really, really good at doing. The main barrier to building these things is what is called decoherence. So remember we said the cat is sealed inside a box, and the minute I look at it, it stops being in this magical mixture of states, and it turns into a natural live cat or a natural dead cat. If the box interacts with anything at all outside it, even a few molecules of air, the same kind of process can occur. It can lose its superposition. It's called decoherence as the superposition seeps out of the box. So research is looking on physical mechanisms to contain a quantum computer. It's a little like nuclear fusion research, where they try and isolate a reaction with magnetic fields and so on. You have to make a place where the computation is getting done and nothing is touching anything from the outside. You can't have any noise coming into the system at all. You might have heard of this company, D-Wave Systems. They have claimed to have built what is called a quantum adiabatic computer. This is actually not a quantum computer, it's a quantum adiabatic computer, which is a different thing. They have made a lot of money selling these to Google and the NSA and a bunch of other places. There is some lively debate over exactly what the quantum capabilities of these things actually are. They are making use of noise in a process called annealing. I'm not going to go into this in detail. They are making a bunch of assumptions about continuous time. You might think you can make your computer do an infinite amount of computation in 1 second, even on a classical machine, just by taking the clock rate up to infinity. You know, if you assume you can do more and more computation per unit of time, then you can make anything run in order 1 time, where the units are seconds. So there's a little bit of those assumptions going on there, and there is still debate about what is happening here. Some of these guys have proposed what's now called Rose's law, saying the number of qubits we've implemented is doubling every 2 years. It's a quantum version of Moore's law. So you can see there is some commercial activity happening here, but it is disputed. It is a very active area of research, mostly in university labs, but sometimes going out into industry as well. So if that wasn't enough, let's do brains. The human brain is the most complex system in the world after the University of Lincoln exam policy. But it has provided inspiration for computer architecture all through its history. If you go right back to Boole and Babbage, they talked about brains. Deep learning has become a huge thing over the last decade. That has encouraged a particular style of computer architecture based on certain very simple models of the brain. I wanted to talk a little bit here about the actual brain. What can we learn from computer architecture by looking at the actual brain? What are the architectural design principles that are manifested here? So as in silicon architecture, I'm going to go through the different levels of abstraction here. At the lowest level, in computer architecture, we've talked about transistors. Okay, a transistor is a switch. So it's got a main input and a main output, and if you activate the switch, then current flows. It's like a water pipe. And we implement these out of semiconductors and silicon-like elements from this part of the periodic table in blue. If you remember how this thing works, it's all to do with balancing chemical forces and electrostatic forces. You remember the movement of electrons across the barrier? We can compare that, not with a neuron, but with what is called an ion channel. This is a subcomponent of a neuron. So this is a whole neuron cell. If we zoom right in on a little tiny bit of that cell, we'll see that the barrier is full of these little proteins called ion channels. Remember, proteins are the things that get made by the RNA. This is the other end of the DNA process. So there are millions, maybe billions of these sitting in a neuron. Each one of these is either going to be on or off. It is going to allow stuff to flow through it. Okay, so it's a hole in the barrier of the neuron, and you can turn them on and off like a transistor. You can switch on or off the flow of these different molecules. Some of them are specialized to allow different kinds of atoms or molecules to flow through them. This is all to do with the balance of chemical forces. It is somewhat like the transistor. We saw this idea of having different atoms around and there being balances of different populations and achieving this chemical electro balance. You get the same idea here. Some of these things are ionized, so there's a positive charge on one side of the wall, negative charge on the other. The cell is trying to maintain that barrier, and there's a tension between the electrostatic forces and the chemical forces. Usually if you put a lot of a chemical in one place, it wants to diffuse, it wants to get mixed up, but if that's competing against an electrical force pushing it away, then you have that kind of balance. Most living objects are made out of a different set of stuff from silicon machines. They're made out of the elements colored green here. They tend to be elements close to the top of the periodic table. These are elements that there are a lot of. If you look at the formation of stars and planets, this is the stuff that tends to get kicked out. It's the stuff that is easy to find floating around in the ocean when you begin to evolve and put simple machines together. So as we built logic gates out of transistors, we can think of building a neuron out of those ion channels, right? This is a whole neuron. It's a brain cell. I found it in some other places, mostly in the brain. But you can find those ion channels all around the body of the neuron. And sometimes we represent the neuron mathematically like this. This is a diagram and then showing an equation, which has some similarity to how we build a logic gate. So let's consider an AND gate. We have two inputs, we do some logic, we create an output, okay? And this is a non-reversible computation. We're throwing information away because you can't reconstruct the input from the output. The inputs and outputs to this are both binary, 0 or 1. That's the same in a neuron. So we're going to put zeros and ones in, and we're going to get a single 0 or 1 coming out of the other end. What you see in a neuron then is a whole bunch of inputs. Each of these, what are called dendrites, these are inputs, so you can put a 0 or a 1 onto any of those. It does a simple computation, and it sends the result out to what is called the axon, and that contains a 0 or a 1 that is the output. So it looks pretty similar to the form of an AND gate, or at least to a big AND gate with lots of inputs all getting ANDed together. A neuron is a little more complex. It's normally represented by this equation. So you take all your inputs, each one has a weight. This is an analog number. You multiply them by the weight, and you add them together, and maybe you add on this thing called a bias, and then you take a function of that. So roughly the weights are saying which inputs you like. Any inputs with a large weight are the ones that the neuron likes, and if it sees enough inputs that it likes, then it will fire. Its output goes to a 1. So you see it's based more on chemistry. It's using these it's using the ion channels inside the cell. It's also using pure chemical messaging between cells. So the axon of one neuron will connect to the dendrite of another neuron, and there's a purely chemical process, which is very slow compared to electricity. So slow that it's amazing how good our brain is compared to a silicon chip, which can run at a much higher clock speed. But it roughly has this same form. It roughly has a bunch of binary inputs and a binary output, and it performs a simple, almost logical function of the inputs to map it to the output. We can compare the wiring in a brain with the wiring in a chip. So we make electronic computers like this. We lay down transistors, we put layers of copper wire on them. This sends electrical messages. Again, every message is a 1 or a 0. We use Boolean logic. This is very fast, very accurate. This is where the axon and the dendrite meet in the neuron cell. So it's where the output of one cell is, we call this synapsing onto the input of another one. So the signal travels kind of as electricity as it goes down the axon using properties of the ion channels. When you get to the end, it's this purely chemical process. The axon of this neuron will release some very small molecules which cross over the gap and they get picked up at the other end. So this is a purely chemical system. Again, it's a binary system. The connection's either made or it isn't. But unlike the copper, it's very slow and very noisy. It's amazing this works as well as it seems to do. In some people's brains, at least. Less well known is the levels of abstraction above this, which are called the microcircuit level. So we've talked about microcircuits in digital logic. So these are things like a simple adder, or maybe a half adder, a register, the kind of things you can build in Logisim in a couple of hours. We've seen that we build CPUs by taking a bunch of these simple machines and putting them together to make these larger structures. But we well understand what the basic structures are. We know what an adder is, we know what a half adder is, we know how to build a register and a RAM, and so on. There may be some equivalent of this level in the cortex of the brain. This is not fully understood. We know some of it. We're working on the rest of it. If we take the cortex, so the cortex is this bit, the outside of the brain that you can see. You will find it is really structured as a two-dimensional sheet. If you imagine a piece of paper scrunched up to make that characteristic brain pattern, that's what you have there. The real topology of it is a 2D sheet. You can take a cortex and flatten it out and see it all spread out in front of you. If you cut through that sheet, you then see there are 6 layers of cortex, and each layer has a different kind of set of neurons in it. And we know something about the types of these neurons, and we know something about their connectivities. There is a structure here that looks similar to the simple machines we build in Logisim and so on. So we know, for example, that data comes in, it arrives in layer 4. This is data from your visual system, audio system, whatever. It goes up to the higher layers. This whole thing is paper thin. Remember, all scrunched together. It goes up to the higher layers, it meets information coming down from more abstract levels, and then it all goes down here to layers 5 and 6. Maybe it meets information propagating over time as well. There's some processing here, and then it gets passed down the cortex. So there's 2 flows of information. One is sending information up from your sensors to your percepts, and the other is sending information back down from your percepts to your sensors. So there are some computational models of this. Some people are proposing this now as a silicon design for future architectures. So for example, Jeff Hawkins has a company called Numenta that he's trying to build these. They're proposing it as an alternative to the deep learning neural networks you see. You could implement this kind of thing either on a GPU or on an FPGA or on a completely custom chip. But nobody completely understands mostly the weights on these connections. We know what kinds of neurons are in each layer. We know which populations of neurons are connected to which. You can see there's different colors, different types of neurons. But we don't have the equipment, the sensors to see exactly what's going on. We don't have a debugger for a cortex to look in there and see exactly which neuron is causing which other one to fire. So there's a lot of speculation here. If you want to start a neuro-inspired company like Numenta, you have to make up a load of stuff. You have to constrain your architecture by the facts we do know about what's connected to what, but then you have to make up a theory of what each layer of this is doing. So some of those people are then feeding back their computer architecture ideas to the neuroscientists. The neuroscientists can run certain experiments to look for things, but it's hard to do science unless you have a theory. You don't know what to look for if you don't have a theory. So what we're seeing now is computer architects who are used to building this kind of thing. They will go out and look at what is known over here, and they try and spot similarities. They say, this looks a bit like this digital logic, this simple machine that I already know how to build. That will create a theory, and you give that theory back to the neuroscientists, and they can try and design an experiment to see if the brain is really doing that. So this is an interesting career choice for computer architects. If you're interested in working with neuroscientists, take what you've learned about architecture and see if you can find similarities in the data from those neuroscience experiments. Whoever figures this out is almost certainly going to get a Nobel Prize. This would be understanding the basic mechanism of the human brain. So it's not easy. A lot of people are trying. So that's the microcircuit level. That's sub-millimeter of a bit of your cortex. Then this is what the whole brain looks like. And we could compare that with, say, the layout of a whole chip. So what's interesting is this two-dimensionality is similar to both. Chips have evolved into these very two-dimensional structures. So unless we get into the silicon cube architectures, we're still very much into routing algorithms, optimal paths around 2D spaces. And maybe it's just coincidence, but it's an interesting coincidence that the brain has also evolved to function as a two-dimensional layout. If you take that cortex of the brain, it looks like a scrunched up piece of paper. You roll it out. It's probably a few meters square of stuff. And within that paper, you see the 6 layers. Imagine taking 6 big chunks of paper and gluing them all together as a stack and then scrunching it up, and you've got a brain. We have some ideas about the functional level of these architectures. Again, we can draw some insight by comparing the two. We know that to build a computer, there's maybe around 50 well-known named areas. These are areas, if you look at a die shot of a CPU, you can try and identify these levels of things, or maybe subcomponents within them. And we have this very serial idea of a CPU and a memory and a bus and an ALU and so on. What we see in the brain is a more inherently parallel architecture. There are similarly around 50 well-known named areas, so you can take that cortex and divide it up into colored bits, and we do have a pretty good idea of, at least at the back of the brain, what each of these bits are doing. It gets more foggy as you go to the front. That's where the really clever stuff seems to be. Roughly, this is the back of the brain, and this is the front of the brain. We know that these areas are functionally connected to each other by sending what look a lot like buses. They send groups of wires from one area to another area in bulk. Some of these really do function like buses. They can be an output of one area, and they can go out as a bus and be connected to by a whole bunch of other areas who are all receiving the same input. But the big difference is that our CPUs are based on this instruction idea. They're based on this very serial Turing machine style idea of running one instruction at a time. You have this whole beautiful physical system, but it only does one thing at once. Whereas here, every module is pretty independent of all the other modules. It's possible to knock modules out of brains and still have the rest of the brain work to different extents. So we see this more instruction-less parallelism happening over there. Okay, a couple of other things about the brain. As well as this beautiful hierarchy in the cortex, we also have subcortical pathways. There seems to be these evolutionary older wires. They look a little bit like IRQs. They're things that just give you an instinct. They trigger something and they say, oi, come and look at this. Maybe these are to do with emotions or intuition or pattern recognition, whereas the main cortex is rational thinking hierarchies. There's also a serial aspect to the brain. You do all that parallel stuff, but your experience of the world is what we call unitary and coherent. It means you only experience a single version of the world. It's a complex state of the world, but you perceive the world in one state at a time, not as a set of different interpretations. And explaining how that serial architecture emerges from the parallel components remains a very, very open research challenge. It seems a little bit like an orchestra with a conductor. These areas are all doing their own things, but something is synchronizing them and coordinating them. Maybe this is the thing we call subjectivity or consciousness, whatever those words mean. The part that sits right at the top of the brain is called the hippocampus. That seems to be where all the things we're perceiving come together. We put them in space and time. If you're interested in some models of that, there's a link to a paper here about it. All right, just to finish, let's go really wacky. Let's go to like 100 millichopras. This guy, Deepak Chopra, is a well-known pseudoscientist. So I'm measuring wackiness in millichopras here. This is all of modern physics, almost. This is called the Standard Model. It's all written as one big equation that describes everything that happens at CERN. We now know there are kind of 17 different particles or fields that interact. We recently found the Higgs boson. There's no way God would have created this. God would not work in base 17. God is going to create 0 and 1, and everything else is going to follow, or at least the power of 2, right? was nice when it was 16. Why did they have to put that thing there? We currently compute mostly with electrons, which are here, but the standard model shows us there are all these other kinds of particles. We've talked a bit about computing with light, with photons. Why not look in the distant future at all this other stuff that is being discovered by CERN and places like CERN? We're only using a few terms in this giant standard model equation to do our computing with. What could we do if we opened up all the other particles there? So there are already engineering efforts to at least to weaponize this. So CERN is a giant particle accelerator. Governments love to fund this stuff because they can use it to build death rays. So in 1990, there was an experiment in space. They took a CERN-like accelerator, put it in a rocket, and tried to use it to zap things in space, or zap from space down to Earth. Everyone's favorite American President, Mr. Trump, is currently funding us to do this again. In 2020, we are going to be putting CERN-like discoveries into space and using it to zap things, maybe on the ground, maybe other things in space. These are examples of engineering with CERN-like technology, but why not do computing with it? Remember these billiard ball computers? We've seen you can make an AND gate by shooting billiard balls. We talked as if these things were macroscopic marbles, but what if they were particles like this from CERN? What if we got it down to this size and shot bosons at each other to create AND gates and OR gates? CERN is all using a theory called quantum field theory. It does not include general relativity. That's the other part of physics. The physics is currently a mess. The gravity people can't fit their models together with the quantum people. Gravity has recently come back into fashion. There was the LIGO experiment very recently has discovered gravitational waves. And so there are propositions for computing with gravity. If you've ever seen the movie Interstellar, you could, for example, park your spacecraft in orbit and go down to a really heavy planet and spend some time on it and then come back to your spacecraft, and time will run at different speeds. So when you come back to your spacecraft, 1 million years has passed there and your NP-hard problem has been solved by the computer. Okay, so this is a simple way of using relativistic effects to speed up computation, at least from your point of view. There are semi-serious proposals for actual warp drives. This is the link to the physics publication about building the Star Trek warp drive. This is a technology, in theory, it maybe works. In practice, you'd need a literally astronomical amount of energy to do it. It apparently gives you faster than light space travel by bending space-time. So you never go faster than light, but you bend space and time so that the places you're going are smaller than everywhere else. So you can go at a slower speed through a shorter piece of time. It's a little like an aeroplane wing where you make the air go at different speeds above and below you. But these ideas feed into what is called hypercomputing. This is relativistic computing. A hypercomputer is something that has powers beyond a church computer. Remember, lambda calculus represents the power of any computing device. And Church's definition was that a computer is something that can simulate another computer. If you can do things like this is called a closed time-like curve. It was shown by Gödel to be consistent with Einstein's relativity. Something looking a lot like time travel is possible, according to this theory. It's called a closed time-like curve. You need a wormhole connecting one part of space and time with another. But if you had a computer going around this loop, you could then solve a bunch of these uncomputable problems. Most uncomputable problems are to do with predicting your own behavior. You give a computer a model of itself. You say, what would this BBC Micro do if this happened? And you give that problem to a BBC Micro, and it can't solve it because it's predicting its own behavior. If you have a closed time-like curve, you don't have to predict the future because it's already happened. You can look in the past and store what happened. You know, am I going to halt or not? You can just look in data you've stored in the past and look it up. And that appears to transcend Church's definition of a computer. This is the kind of thing Turing actually did in his thesis. Church's thesis is Church's thesis. Turing's thesis is about this kind of stuff. It's about computers with infinite resources, infinite programs, infinite axioms. And there's some fascinating, possibly crazy, possibly genius work trying to link Turing's actual thesis to these ideas in relativity. Going way beyond this, these are all the different physical theories around at the moment. It shows you how much computing theory is attached to them. So we know regular computing, we know quantum computing, we know hypercomputing a bit. This is what happens at CERN. Putting these things together in physics is completely crazy. We have theories such as string theory, trying to unify gravity and quantum. Are we going to compute with strings one day? Nobody knows. It's a completely open question. Okay, let's just come back to Earth for the last 2 minutes. Let's talk about your future in architecture then. Architecture is hot again. It was boring for ages. No one wanted to come to architecture classes, and now you're all actually here. It's become more interesting because Moore's law, or whatever form of it, is running out. That creates a crisis and an opportunity. We're in a time, it feels a lot like the 1980s again. We can all actually get into this stuff. We can download the RISC-V stack. You can do this in your bedroom. And there's this mindful movement. Everyone wants to open up the boxes and see what's inside. Hennessy and Patterson just got the Turing Award for this stuff. Now's a good time to throw away all your other textbooks and buy Hennessy and Patterson, which is the definitive, this is the book you have on your desk during your whole career as an architect. Here's how you join the RISC open source community. If you want to go back to your bedrooms now, go to these websites, download it. You can look for internships. We know a lot of these people. Come and talk to us, or just do it anyway. Do it for your project. To continue this, most of the work is in Silicon Valley, which is here. The classic way to work in architecture is to get yourself to Silicon Valley. The classic way to do that is to do a master's degree at either Stanford or Berkeley. And then work for one of the big companies in the valley itself. Doing the MS will help you with your visas and so on. Berkeley is known for RISC-V and Patterson and protests and hippies and LSD, and Stanford is known for Hennessy and MIPS and Sun Microsystems and MBAs and venture capitalists. So choose your style if you go over there. There's a whole bunch of companies. There are 700 startup companies doing architecture in the valley now. This is the new golden age. If you want to stay in the UK, go to Cambridge here, or work for Arm over here, or there are little bits of it elsewhere in the country if you look around, like do optical computing for Thalasis in Wakefield. The rest of you will probably be users of architecture in the future if you don't specialize in it. This is going to be your world. There's going to be the cloud, there's going to be no desktops, there's going to be the Internet of Things, there's going to be robots and sustainable agriculture and smart cities and smart factories and parallel processing and embedded systems. This will be your world. Now go and build it. Thank you. Thank you.